In the vast expanse of the cosmos, we're surrounded by millions of stars and planets, each with its own hidden wonders and secrets waiting to be discovered. Yet beyond their stunning beauty lies a far more unsettling side to these celestial bodies. In the depths of the universe, there are worlds so strange, so terrifying, that they challenge everything we think we know about what it means to be a planet. Picture this: planets where rain doesn't fall in droplets, but in shards of glass, whipping through the atmosphere at speeds so fast they could slice through anything in their path. Or imagine a world cast in perpetual darkness, its surface never touched by the light of its star. There are gas giants with crushing air pressure, so intense that any spacecraft would be pulverized long before landing. Then there are rocky worlds, their landscapes dominated by lakes of molten lava, constantly shifting beneath an unrelenting, fiery sky. These aren't the peaceful blue planets with white clouds or the familiar red neighbors we've long been fascinated with. No, these are the realms of extremes, where the laws of nature create environments so hostile they seem to come straight out of our darkest nightmares. Join us as we embark on a journey through the most terrifying planets in the universe. Take, for instance, Cancri 2b. Known as one of the darkest exoplanets ever discovered, Cancri 2b offers a chilling glimpse into the alien worlds that lurk beyond our solar system. Located approximately 750 light-years from Earth in the constellation Draco, S2b was first identified in 2006 through the Transatlantic Exoplanet Survey, a mission designed to detect planets outside our solar system by observing the dimming of stars when a planet passes in front of them, a method known as the transit technique. Cancri 2b orbits its star every 2.5 days, an incredibly short orbit revealing just how close the planet is to its star, only about 3 million miles away, a distance much closer than Mercury is to the Sun. What makes Cancri 2b truly unique, however, is its shocking lack of reflectivity. Less than 1% of the light that strikes its surface is reflected, making it darker than coal, darker even than any planet or moon in our own solar system. This eerie darkness is due to its atmosphere, which contains light-absorbing chemicals like vaporized sodium and potassium, coupled with an absence of clouds. The result? A planet so dark that it seems almost invisible against the backdrop of space. But darkness isn't Cancri 2b's only terrifying feature. The extreme heat on its surface pushes temperatures above 1,800 degrees Fahrenheit, making it one of the hottest planets ever discovered. Despite its deep blackness, the planet still manages to glow, faintly like the embers of a dying fire, thanks to the intense heat radiating from within. This strange, dim red glow adds an eerie mystique to the planet, captivating astronomers and stargazers alike. The proximity of Cancri 2b to its star also results in tidal locking, a phenomenon where one side of the planet is constantly exposed to the star, basking in unending daylight, while the other side is trapped in eternal night. This division between day and night creates a stark contrast in temperature, which could lead to winds so fierce they defy our understanding of weather. The conditions on Cancri 2b are nothing short of bizarre, with its atmosphere full of metal vapors and no clouds to reflect the light. Some scientists even speculate that it might host clouds made of compounds completely foreign to Earth, a truly alien feature. Studying Cancri 2b gives us a rare opportunity to explore the strange chemistry and physics of exoplanets, providing us with clues about how planets like this form, evolve, and survive. The insights we gain from this research could even help us understand the potential for life in the universe, or, more likely, the absence of it in such extreme conditions. By examining Cancri 2b alongside other exoplanets, scientists can better appreciate the incredible diversity of planetary systems in our galaxy. From dense, stormy atmospheres to barren, rocky wastelands, every new discovery brings us closer to understanding the full range of possibilities for planets beyond our solar system. It's a reminder of just how much there is still to learn as we continue our quest to understand the universe and the countless strange worlds it contains. Cancri 2b, with its remarkable features, stands out as a fascinating subject for future astronomical investigations. As we look to the skies, the James Webb Space Telescope, along with an array of advanced ground-based observatories, are ready to unlock unprecedented views of exoplanets like Cancri 2b. These future observations will offer scientists an opportunity to peer deeper into the planet's atmosphere, uncover its surface conditions, and perhaps even uncover signs of geological activity, providing us with a more detailed portrait of this distant world than ever before. Continuing our journey through the cosmos, we now turn our attention to 55 Cancri, a planet that has long captivated both scientists and the public with its extraordinary characteristics. Located about 40 light-years away in the constellation Cancer, 55 Cancri is a super-Earth, a world that is roughly twice the size of Earth and 8 times its mass. But it's not just the size that makes 55 Cancri so intriguing. Its orbit around its host star, 55 Cancri A, is so close that a full year on this planet lasts just 18 hours, an astonishing contrast to our own 365-day orbit around the Sun. However, what truly sets 55 Cancri A apart from the vast majority of exoplanets is its potential surface conditions, which have led some to refer to it as a diamond planet. Scientists speculate that the immense pressure within this exoplanet could cause carbon to crystallize into diamonds, leading to a world that, in a sense, sparkles with precious gems. While this captivating idea has fired up the imagination, it remains just a hypothesis, one that researchers are eager to test with more advanced tools in the coming years. Equally fascinating is the planet's extreme surface temperature, which soars beyond 4,000 degrees Fahrenheit. At such temperatures, 55 Cancri A is far from a hospitable environment by our standards. The blistering heat, a direct result of its proximity to its star, ensures that its atmosphere, if it exists, would be unlike anything we observe in our solar system. The gases may exist in a supercritical state where they blur the lines between gas and liquid, presenting a radically different climate and environment compared to any planet in our solar system. As we dive deeper into the mysteries of 55 Cancri, it becomes clear that this planet challenges our fundamental understanding of planetary systems. Orbiting just 1.5 million miles from its host star, 55 Cancri belongs to a category of exoplanets known as ultra-short-period planets. This extreme proximity means that the tidal forces between the planet and its star are so intense that the planet is likely tidally locked. One side perpetually facing the star in unyielding daylight, while the other side is cast into eternal darkness. The stark contrast between these two hemispheres has profound implications for the planet's climate. Scientists theorize that the massive temperature differential could give rise to supersonic winds, transporting heat from the scorching day side to the frigid night side. This extreme weather system could drive a dynamic, constantly shifting atmosphere, one unlike anything we have witnessed in our own solar system. Adding yet another layer of intrigue to 55 Cancri is the composition of its atmosphere. Early observations suggested the presence of water vapor, but more recent studies have pointed to a hydrogen-rich atmosphere with traces of hydrogen cyanide, a potential indicator of carbon-rich conditions. These findings only intensify the speculation that 55 Cancri could indeed be a diamond planet, its carbon-heavy interior transformed under crushing pressure into glittering gems. The possibility of an atmosphere rich in carbon compounds not only intrigues scientists, but also sparks the imagination about what other extraordinary worlds may be out there waiting to be discovered. With every new observation and hypothesis, 55 Cancri pushes the boundaries of our knowledge, hinting at a universe full of wonders that we have yet to fully comprehend. Embarking deeper into the frontier of exoplanet exploration, we encounter one of the most intriguing worlds in the galaxy, Gliese 581c. Discovered in 2007, this planet orbits the red dwarf star Gliese 581, located roughly 20 light-years away in the constellation Libra. But what makes this exoplanet particularly fascinating is its position within its star's habitable zone, a region where conditions may allow for liquid water to exist, the essential ingredient for life as we understand it. Gliese 581c, a super-Earth about 1.5 times the size of our planet, is no ordinary exoplanet. With a mass roughly 5.5 times that of Earth, it boasts a gravity much higher than ours, which could profoundly influence its atmosphere and any potential forms of life. This world completes an orbit around its host star in just under 13 days, a remarkably short period that places it in close proximity to Gliese 5 and 81. The implications of this proximity are not only tantalizing, but raise questions about the planet's climate and its suitability for life. One of the most captivating aspects of Gliese 581c is the possibility that it may harbor liquid water. This idea hinges on the delicate balance of temperature and atmospheric pressure, a condition that could allow for oceans, rivers, or lakes, worlds teeming with life, much like our own. Yet there's a challenge. The planet's close orbit suggests it might be tidally locked, meaning one side could constantly face the star while the other remains in perpetual darkness. Such an arrangement could create extreme temperature contrasts across the planet, with one side too hot and the other too cold for water to remain liquid. However, despite these challenges, the potential of Gliese 581c being within its star's habitable zone sparks a new frontier in scientific exploration. This discovery not only ignites the imagination, but propels us further in our quest to understand the conditions necessary for life to thrive on other worlds. The study of Gliese 581c, alongside its sibling planets in the Gliese 581 system, offers a vast and intricate canvas for investigating the diversity of planetary environments. The concept of a tidally locked world like Gliese 581c raises fascinating possibilities for climate and weather patterns. If the planet has an atmosphere, scientists speculate it could circulate heat from the star-facing side to the dark side, potentially creating a more stable climate than we might expect. This might lead to the formation of a twilight zone, an area where temperatures are just right for liquid water and possibly life. Yet the challenges of exploring a planet so distant from Earth are considerable. Gliese 581c lies far beyond the reach of current technology. And while we continue to push the boundaries of our observational capabilities, we are still limited in how much we can know for certain. Nevertheless, astronomers are working on groundbreaking missions to deploy telescopes capable of directly observing exoplanets, analyzing their atmospheres for key indicators of life, water vapor, oxygen, methane, and other gases that could hint at biological activity. These observations may not confirm life outright, but they will provide vital clues about whether planets like Gliese 581c can sustain conditions conducive to life. Moreover, the study of Gliese 581c contributes to our broader understanding of red dwarf stars, some of the most common stars in the Milky Way. Their long lifespans offer a stable environment for habitable planets. But with that stability comes a risk. Red dwarfs are known for their violent flares, which could strip away the atmospheres of planets orbiting too closely, making it difficult for life to thrive. In the quest for answers, Gliese 581c represents both a mystery and a stepping stone, a glimpse into what might be possible on distant worlds, waiting to be uncovered by future generations of explorers. Exploring planets beyond our solar system offers more than just a glimpse into the unknown. It holds the potential to answer one of humanity's most profound questions. Are we alone? Among the most captivating objects in this search is Proxima Centauri b, an exoplanet orbiting Proxima Centauri, the closest known star to our Sun, just 24 light-years away. Discovered in 2016, this intriguing world has become a focal point for astronomers as it sits within the habitable zone of its parent star, where temperatures could support liquid water, one of the key ingredients for life. Yet the possibilities presented by Proxima Centauri b come with challenges, and the scientific community is keen to unravel its mysteries. Proxima Centauri b, approximately 1.3 times the mass of Earth, is believed to be a rocky planet, much like our own. Its proximity to the star, however, means it orbits in just 2 Earth days, making it a prime candidate for tidal locking, a phenomenon where one hemisphere always faces the star while the other remains in perpetual darkness. The impact of this on the planet's climate and potential habitability is profound. On one hand, the day side may experience extreme heat, while the night side could be plunged into freezing conditions. Such a stark divide may pose significant challenges to the development of stable climates or life-supporting environments. However, the most significant obstacle facing Proxima Centauri b is the temperament of its host star. Red dwarf stars like Proxima Centauri are known for their stellar flares, powerful outbursts of energy that can unleash intense radiation. This unpredictable nature raises concerns about the planet's ability to maintain a stable atmosphere. Powerful flares could strip away any protective atmosphere, leaving the surface exposed to damaging radiation. Despite this, there is hope. Scientists theorize that should Proxima Centauri b possess a strong magnetic field, similar to Earth's, it could act as a shield, protecting the planet from these harmful bursts and maintaining the potential for life. Beyond radiation, the question of atmosphere is crucial. The atmosphere not only serves as a barrier against harmful radiation, but also plays a key role in regulating temperatures and supporting the water cycle. If Proxima Centauri b has the right atmospheric conditions, it could potentially support liquid water on its surface, an exciting possibility for the search for life. Yet this prospect depends on many factors, including the planet's composition and whether it has developed a stable atmosphere over time. Without the right protection, the intense radiation from its parent star could prove too much, hindering the development of life. The climate dynamics of a tidally locked planet like Proxima Centauri b are also a subject of intense speculation. On such a planet, the boundary between the light and dark sides, the terminator zone, could represent a temperate region where liquid water might persist, creating a delicate balance conducive to life. This zone would likely experience moderate temperatures, not too hot from the star's influence, and not too cold from the endless night. If this region exists, it could host an environment where life, as we know it, could take root. As astronomers continue to study Proxima Centauri b, future missions are being developed with cutting-edge technology to probe deeper into the planet's atmosphere. Spectroscopy, which involves studying the light from the star passing through the planet's atmosphere, could reveal traces of molecules like oxygen, carbon dioxide, and methane, all of which are linked to biological activity. These tiny chemical signatures could point to the presence of life, sparking further exploration and intrigue. But even with advanced tools, sending a probe to Proxima Centauri b remains decades away. However, missions like Breakthrough Starshot aim to send small, light-powered spacecraft to the Alpha Centauri system in the coming decades. These missions represent an ambitious leap in interstellar exploration, offering the possibility of direct data and insights from Proxima Centauri b, and perhaps one day answering the question of whether life could exist beyond our world. In the end, Proxima Centauri b represents not just a single planet, but a symbol of our endless curiosity and drive to understand the universe. Every new discovery, every breakthrough in technology brings us one step closer to understanding the vast and potentially life-rich cosmos that surrounds us. Venturing further into the cosmos, we encounter PI Mensae c, a fascinating exoplanet that carves out its own unique niche within the expanding catalog of celestial bodies. Situated 60 light-years away in the constellation Mensa, PI Mensae c orbits its host star, PI Mensae, a distant yet compelling point of focus for astronomers. Its discovery in 2018, announced through data from NASA's Transiting Exoplanet Survey satellite TESS, represented a monumental step forward in the search for exoplanets, unveiling yet another intriguing world beyond our own. PI Mensae c belongs to the category of super-Earths, planets that boast masses greater than Earth's, but are still far lighter than the ice giants Uranus and Neptune. At approximately 4.82 times Earth's mass, it presents a striking contrast to the rocky worlds we know so well. Yet, what truly sets it apart is its orbital characteristics. Completing a full orbit in just 6.27 days, PI Mensae c resides much closer to its host star than Mercury does to our Sun, giving it an extremely short and rapid year. This proximity to its star brings with it both promise and mystery, as the planet's intense closeness suggests a world that could experience extreme radiation, potentially stripping away its atmosphere or affecting its habitability. Beyond its physical attributes, PI Mensae c's most fascinating feature may lie within the context of its solar system. Orbiting alongside the gas giant PI Mensae b, which was discovered in 2001, this system provides a rare opportunity to explore the dynamics of a multi-planet setup. The stark differences between the super-Earth and the gas giant offer astronomers a rich field for studying planetary systems, one where such contrasting planetary types coexist. The contrasting compositions, varying orbits, and potentially divergent atmospheres present an invaluable dataset for understanding the variety of planetary environments scattered across the Milky Way. Yet, questions about PI Mensae's potential for life remain largely unanswered. The intense stellar radiation it receives may hinder the development of a stable atmosphere, but without detailed atmospheric studies specifically focusing on water vapor or carbon dioxide, scientists cannot yet rule out the possibility of habitability. The search continues, offering tantalizing hints of what might be discovered in the future. And then there is Fomalhaut b, a planet whose enigmatic nature has captured the imaginations of astronomers and stargazers alike. Initially spotted in 2008 by the Hubble Space Telescope, Fomalhaut b was one of the first exoplanets to be directly imaged, providing an unprecedented look at a world beyond our solar system. For a brief moment, it seemed as though we had a new planet to study, a distant world caught in the act of its cosmic dance around its host star, Fomalhaut. However, as is often the case with the mysteries of the universe, the story did not end there. Fomalhaut b's odd behavior soon caused confusion. Unlike other planets, it did not emit the infrared radiation expected of a celestial body. Infrared radiation is essential for determining the temperature, size, and composition of a planet, yet Fomalhaut b remained an infrared enigma. As additional observations came in, the exoplanet's existence became increasingly difficult to confirm. It seemed to appear and disappear in different datasets, acting more like a ghost than a solid planetary object. This led to a dramatic shift in scientific opinion. In 2012, some researchers proposed a startling hypothesis. Perhaps Fomalhaut b was not a planet at all. Instead, they suggested it might be a vast cloud of dust, the remains of a catastrophic collision between two icy bodies. This theory imagined a cosmic demolition derby, where the aftermath of the collision left behind a transient cloud orbiting the star Fomalhaut, offering only fleeting glimpses of its existence. But the mystery didn't stop there. The debate continued to evolve. Some astronomers still clung to the idea of Fomalhaut b being a planet, albeit one obscured by a massive dust cloud. This dust could have resulted from a huge ring system or perhaps the aftermath of an extraordinary impact, which might explain its strange behavior. The possibility that Fomalhaut b might be a world unlike anything we've ever encountered is tantalizing, keeping the door open for further exploration. The story of Fomalhaut b is a testament to the ever-evolving nature of scientific discovery. It is a tale of new astronomical techniques, persistent curiosity, and the willingness to entertain bold ideas. The ghostly world that may or may not be a planet continues to inspire debate, and it is through such debates that the boundaries of human knowledge are continually pushed. In the end, the pursuit of understanding these distant worlds, whether it's PI Mensae's super-Earth mystery or the ghostly enigma of Fomalhaut b, reflects our relentless drive to explore the cosmos. One discovery, one question at a time. After its initial detection, Fomalhaut b quickly became more than just an astronomical object. It sparked a wave of debate and innovation, propelling astronomers to push the boundaries of their observational methods. This discovery was not just a step forward in understanding our cosmic neighborhood, but a catalyst for advancements in the very technologies used to explore the vastness of space. The Hubble Space Telescope, with its crystal-clear view of the universe, free from the atmospheric distortions of Earth, became a key player in unraveling the mystery of Fomalhaut b. Yet, its story didn't end there. The unique nature of this celestial body drove scientists to explore new, unconventional avenues of investigation. Dynamic imaging techniques and infrared observations through both space and ground-based telescopes added multiple layers of complexity to the story of Fomalhaut b. These innovations, forged in the pursuit of understanding this elusive target, demonstrate the multifaceted approach necessary to study such enigmatic objects. Fomalhaut b's allure is not just in its own mystery, but in its ability to highlight a broader theme in the field of astronomy: the hunt for exoplanets and the quest to understand the conditions that might harbor life. Every discovery, no matter how strange or anomalous, brings us a step closer to answering the most fundamental questions. What is our place in this vast universe? Could there be other worlds out there, teeming with life, waiting to be discovered? The case of Fomalhaut b, with its contested nature and the unresolved questions surrounding its existence, is a stepping stone in this grand pursuit. It challenges our understanding of planet formation, the diverse configurations of planetary systems, and the potential for habitable worlds beyond the familiar boundaries of our solar system. Its story is a reminder that the universe is far from static. If Fomalhaut b indeed resulted from a colossal cosmic impact, it's a testament to the constant reshaping of galaxies on cosmic timescales. The possibility that new worlds might form from the debris of such catastrophic events, or that planets could be obscured by thick clouds of dust, expands our understanding of planetary evolution and survival in the harsh, unforgiving environment of space. Then there is the tale of Methuselah, an ancient star that exists far beyond the edges of conventional astronomical understanding. Methuselah's story isn't just about its age, it's about the paradox it presents to scientists. With an estimated age of 14.5 billion years, it appears to be older than the universe itself, which, according to current cosmological models based on the Big Bang theory, is about 13.8 billion years old. This seeming contradiction has mystified astronomers for years by raising important questions about how we measure the age of stars and the reliability of our cosmic models. The mystery of Methuselah lies in the method used to estimate its age, by studying the star's composition and motion. Much like aging humans, stars evolve over time, and by analyzing a star's chemical makeup, particularly its metallicity, the amount of elements heavier than hydrogen and helium, astronomers can infer its age. Methuselah, with its extremely low metallicity, hints at a formation in the universe's infancy when heavier elements were scarce. Its trajectory through the galaxy, along with its velocity, further suggests it belongs to the halo of the Milky Way, a population of some of the oldest stars in our galaxy. Yet the apparent age discrepancy of Methuselah has sparked heated debates within the scientific community, forcing a reevaluation of the methods used to measure stellar ages. This age paradox exemplifies the dynamic, self-correcting nature of science, where even anomalies can challenge accepted theories and pave the way for new understandings. As scientists delve deeper into the possible causes of this age discrepancy, they have begun refining their models of stellar evolution, adjusting for factors like initial star composition and environmental influences. Though these refinements have narrowed the gap, Methuselah's age still places it among the oldest objects in the universe, standing as a cosmic relic from a time when the universe was still in its infancy. WASP 12b, a distant, enigmatic world lurking far beyond the familiar reaches of our solar system, challenging everything we thought we knew about planetary systems. Discovered in 2008, this alien world orbits the star WASP 12, positioned roughly 600 light-years away in the constellation Auriga. But what truly sets WASP 12b apart from the countless exoplanets cataloged over the years is its extreme nature. It is a hot Jupiter, a gas giant that orbits perilously close to its star, resulting in harsh, extreme atmospheric conditions unlike any we've encountered. Nearly 1.4 times the mass of Jupiter, WASP 12b completes its orbit in just over a single Earth day. Its extreme proximity to its star causes surface temperatures to surge beyond 2,200 degrees Celsius, a staggering heat that has profound effects on its atmosphere. Rather than maintaining a symmetrical spherical shape like most planets, WASP 12b is distorted, elongated by the intense gravitational forces at play. The planet's blistering temperatures also create a fascinating phenomenon. Metals such as iron and magnesium, which would normally condense into clouds on cooler gas giants, instead remain in gaseous form, swirling through the atmosphere. But the story of WASP 12b doesn't end there. The gravitational forces exerted by its host star are so powerful that they are slowly pulling the planet closer, in an inexorable journey toward eventual consumption. While this catastrophic end is not imminent, the process offers scientists a unique glimpse into the inevitable fate of planets locked in tight orbits with their stars, shedding light on the natural life cycle of such distant worlds. Moreover, WASP 12b plays a pivotal role in advancing our understanding of planetary atmospheres. Thanks to its position and behavior, scientists have been able to observe and analyze its atmosphere through the transit method. where the planet crosses in front of its star from our vantage point, allowing astronomers to study the starlight that filters through its atmosphere. These observations have uncovered remarkable insights into the composition of WASP-12b, revealing much about the chemical makeup of other hot Jupiters and planets in similar configurations. The discovery of WASP-12b itself came through the Wide-Angle Search for Planets (WASP) project, a ground-based initiative focused on detecting exoplanets beyond our solar system. The transit method used by WASP involves meticulously monitoring the brightness of stars, detecting the periodic dips in luminosity that occur when a planet transits across the face of its star. In the case of WASP-12b, these dimming events occurred every 1 days, the time it takes the planet to complete a full orbit. The distinct pattern of brightness fluctuations allowed scientists to confirm the planet's existence and measure key details about its size and orbit. Subsequent spectroscopic observations, which measured the subtle gravitational influence of WASP-12b on its star, further cemented the planet's characteristics, including its mass. The discovery of WASP-12b added to the growing collection of exoplanets that are reshaping our understanding of how planets form and evolve, especially those that exist in close, tight orbits with their stars. It also demonstrated the effectiveness of ground-based telescopes and the transit method, pivotal tools in the rapidly expanding field of exoplanet research, a field that continues to redefine our place in the cosmos since the first exoplanets were detected in the 1990s. Kelt 9b, a name that echoes through the cosmos, revealing the extraordinary and the unknown. Discovered by the Kilodegree Extremely Little Telescope, or KELT survey, this enigmatic world orbits a star located 670 light-years away in the constellation Cygnus. While the planet's massive size, comparable to Jupiter's, immediately captivates, it's the incredible extremes of its environment that make Kelt 9b truly one of a kind. Kelt 9b is no ordinary exoplanet. Orbiting a blue A-type star, one of the hottest types of stars known to host planets, its very existence challenges what we thought we knew about planetary systems. Daytime temperatures on Kelt 9b rise above 4,300 degrees Celsius, far hotter than many stars themselves, making it the hottest exoplanet ever discovered. And with an orbit that takes only 1.5 days to complete, the planet is locked in a relentless, ultra-short period orbit, feeling the intense heat and radiation from its star with every rotation. Such conditions would be unimaginable in our solar system, yet here, on Kelt 9b, they shape the very fabric of its atmosphere. The star's ultraviolet light is so intense that it's capable of tearing molecules apart, creating a barren atmosphere where few chemical reactions can occur. Instead, the planet's atmosphere is composed predominantly of atoms, a state so unusual that it has become a focal point for astronomers. For researchers, Kelt 9b offers a rare laboratory to study atmospheric chemistry under some of the most extreme conditions in the universe. The atmosphere of Kelt 9b also harbors ionized metals, such as iron and titanium, gases that defy our traditional understanding of planetary atmospheres. These metals, heated to the point of ionization by the planet's scorching temperatures, reveal insights into the planet's dynamic atmospheric processes and the chemical reactions that take place in its violent environment. But there's more to the story of Kelt 9b. As the planet orbits so close to its star, it experiences immense tidal forces, creating a distorted, elongated shape. These gravitational interactions, however, are not just shaping the planet physically. They are also causing the orbit of Kelt 9b to decay slowly but surely. Over time, this spiral toward its star will only intensify the heating, stripping away more of the planet's atmosphere. In the end, Kelt 9b may be consumed by its star, marking the inevitable and dramatic conclusion of its existence. This process offers a glimpse into the life cycle of exoplanets, one that unfolds quickly and violently. In addition to the potential loss of its atmosphere, Kelt 9b's extreme conditions also give rise to observable atmospheric escape. The heat and radiation from its star are so powerful that they strip away the planet's atmosphere, atom by atom, leaving a comet-like tail of gas trailing behind. This visual phenomenon is a direct testament to the planet's harsh environment, where the very building blocks of its atmosphere are being blasted into space. Yet, there's still a mystery that remains unsolved: the curious case of Kelt 9b's night side. While the planet's day side is an inferno of blistering heat, the night side, though still extremely hot, is significantly cooler. This discrepancy raises questions about how heat is distributed across the planet's atmosphere. How do winds and jet streams work in such an extreme environment? Can complex atmospheric dynamics evolve here in a place where the forces of nature seem to stretch the limits of possibility? The study of Kelt 9b is not just a study of one unique exoplanet, but a key to understanding exoplanetary atmospheres as a whole, particularly those orbiting close to their stars. The knowledge gained from Kelt 9b's strange and volatile nature challenges existing models of planetary science, driving astronomers to create new theories that account for the forces at play in such extreme environments. In the end, the more we learn from this blazing world, the more we understand the wild diversity and unpredictability of planetary systems in the cosmos. Continuing our voyage through the vast expanse of space, we encounter a fascinating world, Kepler 10b. Discovered by the Kepler Space Telescope, a mission dedicated to identifying Earth-like planets in habitable zones, Kepler 10b resides approximately 560 light-years away in the constellation Draco. This exoplanet is a remarkable landmark in the exploration of distant worlds, holding the title of one of the first confirmed rocky planets outside our solar system. It provides us with an unprecedented window into the diverse array of planetary compositions that exist beyond the boundaries of our celestial neighborhood. But Kepler 10b is no ordinary planet. With a mass 3.3 times that of Earth, it orbits its star at an astonishingly close distance, more than 20 times nearer than Mercury is to our Sun. This extreme proximity causes a year on Kepler 10b to last a mere 0.8484 Earth days. The result? Temperatures on its surface soar beyond 1,003 degrees Celsius, around 2,372 degrees Fahrenheit, a furnace-like environment where life as we know it would be impossible. Its surface is believed to be molten in places, possibly even hosting oceans of lava, constantly reshaped by the intense heat from its nearby star. The discovery of Kepler 10b marked a pivotal moment in the search for exoplanets. It was the first planet found by the Kepler mission to have both its size and mass precisely measured. This achievement allowed scientists to calculate its density and confirm its rocky nature, proving that planets of this type exist beyond our solar system. This milestone highlighted the capability of modern technology to not only detect, but also study distant planets in greater detail. In studying Kepler 10b, we uncovered deeper questions about the formation of planets in distant solar systems. The transit method, which detects slight dimming of a star's light as a planet passes in front of it, played a key role in unveiling the secrets of this planet. It's a technique that has revolutionized exoplanet research, allowing us to learn about a planet's composition, atmosphere, and physical characteristics, offering a promising future for further discoveries. Kepler 10b's proximity to its star leads us to wonder about the forces that shaped it. How did it end up so close to its parent star? Could it have migrated inward from a more distant orbit over millions of years, a journey that might have altered its composition and surface features? This theory forces us to reconsider our understanding of planetary system dynamics and the powerful forces that govern their evolution. While Kepler 10b itself is inhospitable, its discovery offers hope for finding planets in other solar systems where conditions might support life. The techniques that enabled us to study this planet are part of the broader mission to detect Earth-like, potentially habitable planets elsewhere in the cosmos. The search for such worlds continues to drive scientists and ignite the curiosity of the public, propelling us deeper into the quest for answers about life beyond Earth. Shifting our focus to a more familiar world, we now turn our attention to Venus, Earth's enigmatic neighbor. As the second planet from the Sun, Venus holds a unique place in our understanding of planetary science. Despite being similar in size and composition to Earth, Venus is a stark contrast in terms of surface and atmospheric conditions. Venus's proximity to the Sun makes it the hottest planet in our solar system. With average surface temperatures around 465 degrees Celsius, 869 degrees Fahrenheit, it's a world where heat reigns supreme. This extreme heat results from the planet's thick atmosphere, composed predominantly of carbon dioxide along with clouds of sulfuric acid. These gases create a runaway greenhouse effect, trapping the sun's heat and causing surface temperatures to soar. Though often called Earth's twin because of their similar size and structure, Venus is a world where everything is turned upside down. Its rotation is slow, taking around 243 Earth days to complete one full spin on its axis. And intriguing still, this rotation is in the opposite direction of most planets in the solar system, including Earth. On Venus, the sun rises in the west and sets in the east. Its orbital period around the sun is shorter, lasting only 225 Earth days. The study of Venus has presented numerous challenges due to its harsh environment. Soviet Venera missions in the 1970s and 1980s were the first to send back images of its surface, revealing volcanic plains, massive mountain ranges, and a world constantly reshaped by geological activity. Some scientists believe that Venus may still be geologically active, with recent volcanic activity possibly contributing to its scorching surface temperatures. An intriguing phenomenon associated with Venus is the ashen light, a faint illumination observed on the planet's dark side when viewed from Earth. This mysterious glow has captivated astronomers for centuries, with theories attempting to explain its origin. Venus's thick cloud cover also reflects sunlight so efficiently that it has earned the title of the third brightest object in our sky, outshone only by the sun and the moon. As we continue to explore Venus and other planets in our solar system and beyond, we uncover more about the complex and diverse nature of the worlds that surround us. These planets, whether inhospitable like Kepler-10b or mysterious like Venus, reveal the vastness of our universe and the untold stories that await discovery. And there, in the furthest reaches of our solar system, lies Neptune, silent, steadfast, a sentinel of the cosmic deep. As the eighth and most distant planet, Neptune stands alone after Pluto's reclassification as a dwarf planet. Discovered in 1846, this enigmatic world was foretold mathematically before it ever revealed itself through the lens of a telescope, a stunning affirmation of the power of Newtonian mechanics. Neptune's discovery marks a key moment in the evolution of our understanding of the universe. With a diameter of approximately 49,244 kilometers, 30,598 miles, Neptune is 4 times wider than Earth, making it the smallest of the gas giants. Yet beneath its vast size lies a dense, complex atmosphere, primarily composed of hydrogen and helium, tinged with methane, which gives the planet its characteristic blue hue. Orbiting the Sun from an average distance of 4.5 billion kilometers, about 2.8 billion miles, Neptune takes 165 Earth years to complete a single orbit. To put it in perspective, the planet has only completed one full revolution since its discovery. Despite its frigid distance from the Sun, Neptune is a planet of dynamic energy. Its atmosphere is anything but passive. Storms swirl relentlessly across its surface, propelled by the fastest winds in the solar system, reaching speeds of 2,100 kilometers per hour, around 1,300 miles per hour. These weather patterns, however, are not driven by the sun's faint rays, but by the planet's internal heat, a fascinating anomaly that offers tantalizing clues about Neptune's internal dynamics. The planet's magnetic field further defies expectations. Tilted at an unusual angle relative to its rotational axis and offset from its center, Neptune's magnetic field mirrors that of its neighboring ice giant, Uranus. This strange magnetic alignment hints at the planet's mysterious internal structure and heat distribution, raising questions about the forces that shape the deep interior of this distant world. Neptune's presence is marked not only by its atmospheric activity, but also by its faint system of rings and its 14 known moons. Among these moons, Triton stands out. A curious object, Triton orbits Neptune in a retrograde direction, opposite to the planet's rotation, suggesting that it may have been captured by Neptune's gravity long after the planet's formation. Triton is also geologically active, with cryovolcanoes erupting nitrogen gas and dust, creating a thin atmosphere rich in nitrogen. Our exploration of Neptune remains limited, though the Voyager 2 spacecraft provided a wealth of data during its flyby in 1989. The images and measurements gathered by Voyager revealed Neptune as a world of swirling clouds, high-altitude ice crystals, and dark spots, evidence of powerful storm systems. The information Voyager 2 delivered laid the groundwork for future missions that may unlock even more secrets about Neptune, further illuminating our understanding of the outer solar system and the forces that shape it. Uranus, the seventh planet from the Sun, is a celestial enigma that defies many of our expectations. Discovered in 1781 by the pioneering astronomer William Herschel, it was the first planet to be found using a telescope, expanding the boundaries of the solar system and our understanding of the cosmos. Unlike the rocky worlds closer to the Sun or the more familiar gas giants like Jupiter and Saturn, Uranus is categorized as an ice giant. Its composition is dominated by a mixture of water, ammonia, and methane ices, all enveloped by a thick layer of hydrogen and helium. But it is Uranus's rotation that captures the imagination. The planet spins on its side with an axial tilt of about 98 degrees. This extreme tilt means that Uranus rolls around the Sun, rather than orbiting in the traditional upright manner. As a result, the planet experiences extreme seasonal shifts, with each pole bathed in sunlight for about 42 years before plunging into 42 years of darkness. Scientists believe this strange axial orientation was caused by a colossal collision with an Earth-sized object early in the planet's history. Uranus is encircled by a ring system, thin and dark, not as spectacular as Saturn's, but still an intriguing feature. These rings were discovered in 1977, providing a glimpse into the many mysteries still awaiting discovery in the outer solar system. Accompanying the planet are 27 known moons, each named after characters from the works of William Shakespeare and Alexander Pope, lending a cultural richness to Uranus's scientific allure. Although Uranus has only been visited once by a spacecraft, the Voyager 2 mission in 1986, the data collected has shed significant light on the planet. Its calm, pale cyan appearance, a result of methane in its atmosphere, belies the turbulence beneath. The planet's winds are among the fastest in the solar system, reaching up to 900 kilometers per hour, 560 miles per hour, challenging our understanding of atmospheric dynamics in the outer solar system. Despite its distant and mysterious nature, Uranus remains a key puzzle in our study of the outer planets, a world of contrasts where extreme tilt, fierce winds, and icy compositions converge to create one of the most intriguing planets in our celestial neighborhood. Pluto, once known as the ninth planet from the Sun, has sparked the curiosity and imagination of both astronomers and the general public ever since its discovery by Clyde Tombaugh in 1930. Positioned on the farthest fringes of our solar system, Pluto lies in the Kuiper Belt, a mysterious, icy region teeming with frozen bodies and ancient remnants from the solar system's formation. In 2006, the International Astronomical Union, IAU, redefined the boundaries of what constitutes a planet, and Pluto was reclassified as a dwarf planet. While this new label may have diminished its planetary status, it has only fueled greater scientific intrigue, as Pluto continues to embody the unknowns that reside at the very edge of our solar system. With a diameter of just 2,377 kilometers, 1,477 miles, Pluto is far smaller than Earth's moon. Its orbit is highly elliptical, which means that over the course of its 248 Earth-year journey around the Sun, it sometimes ventures closer to the Sun than Neptune, before retreating to its more distant position. This strange orbit results in dramatic environmental fluctuations, adding to the complexity of Pluto's geological and atmospheric behavior. The surface of Pluto is an astonishingly varied landscape, featuring vast plains, towering mountain ranges, and deep, winding valleys. One of its most iconic features is Sputnik Planitia, a massive, heart-shaped glacier made primarily of nitrogen ice. This region suggests that Pluto is not just an ancient frozen world, but one that is still geologically active beneath its icy exterior. Mountains of water ice, which behave more like rock due to the extreme cold, further hint at hidden geological processes that we have only just begun to understand. Despite its distant location, Pluto boasts a thin atmosphere primarily composed of nitrogen with traces of methane and carbon monoxide. As Pluto moves farther from the Sun, its atmosphere freezes, falling to the surface as snow, a fascinating seasonal cycle that provides a unique opportunity to study planetary atmospheres in the harshest of environments. Pluto's 5 moons, Charon, Styx, Nix, Kerberos, and Hydra, add a layer of complexity to its story. Charon, the largest of these moons, is so massive in comparison to Pluto that the two bodies actually orbit a point in space between them, creating a system that some scientists describe as a double dwarf planet. The gravitational interaction between Pluto and Charon is both fascinating and unique, offering insights into how celestial bodies can coalesce into a delicate balance. The arrival of New Horizons in 2015 brought humanity's first close-up images of Pluto, unveiling unprecedented details of its surface, atmosphere, and moons. The spacecraft's flyby revealed a world far more complex, dynamic, and geologically active than anyone had previously imagined, sparking a renewed sense of wonder about what lies at the outermost edges of our solar system. Jupiter's moon, Io, stands as one of the most extraordinary and dynamic bodies within our solar system, captivating astronomers with its violent, ever-changing landscape. Discovered by Galileo Galilei in 1610, Io is the innermost of Jupiter's 4 largest moons, known as the Galilean moons. But it is its unparalleled volcanic activity that truly sets it apart. With more than 400 active volcanoes across its surface, Io is the most volcanically active celestial body known to humankind. The source of this relentless geological activity lies in the powerful tidal forces exerted by Jupiter and the gravitational interactions with its neighboring moons, Europa and Ganymede. These forces induce immense tidal heating within Io, causing the moon's interior to flex and stretch, keeping its mantle and core in a constant molten state. Io's surface is a stunning patchwork of sulfur and sulfur dioxide frost, with vibrant colors ranging from yellow and red to white, black, and green. This diverse palette of hues is the result of continuous volcanic eruptions that constantly reshape the moon's surface. Plumes of material can erupt up to 500 kilometers, 310 miles, into space, depositing vast quantities of sulfur in a variety of forms, from volcanic flows to explosive eruptions that carve massive basins across the surface. Io's extreme volcanic activity and colorful, ever-shifting terrain make it one of the most intriguing moons in our solar system, offering a fascinating glimpse into the forces that shape planetary bodies in real time. Despite its incredibly hostile environment, Io plays a pivotal role in shaping our understanding of geological processes beyond Earth. It forces scientists to rethink everything they thought they knew about planetary and moon formation, the necessary conditions for volcanic activity, and even the possibilities for life in the harshest of environments. But Io is more than just a mysterious moon. It is a key to understanding Jupiter itself. The study of this fascinating moon has revealed the intricate magnetic and gravitational interactions within the Jupiter system, especially how Io generates an electric current known as the Io flux tube. This current, which is channeled into Jupiter's magnetic field, gives rise to the planet's spectacular auroras. The most significant revelations about Io have come through flyby missions, such as the Voyager spacecraft in the late 1970s and the Galileo orbiter in the 1990s and early 2000s. These missions peeled back the layers of Io's complex and ever-changing environment, showing a world where the ground is perpetually in motion. Continuing our exploration of Io, we delve deeper into the striking volcanic activity that makes this moon unlike anything else in the solar system. The constant volcanic eruptions on Io are not just breathtaking natural phenomena. They offer scientists an unparalleled opportunity to observe the internal mechanics of a celestial body. The heat generated by tidal forces within Io's interior fuels these frequent eruptions, constantly reshaping the landscape. This ongoing process presents a live laboratory for understanding how volcanic activity can alter a body's surface, atmosphere, and even its habitability potential. One of the most stunning discoveries on Io is its lava lakes and vast molten rock flows that stretch across the surface. These features are a clear indication of Io's extreme internal heat, with some areas estimated to reach temperatures over 1,200 degrees Celsius, around 2,192 degrees Fahrenheit. The lava, rich in silicates and sulfur compounds, offers scientists a glimpse into the moon's unique formation and the elemental composition of the outer solar system. Unlike the basaltic flows we see on Earth, Io's molten rock reveals the raw materials that make up the building blocks of moons and planets in the more distant reaches of space. Yet, Io's influence does not stop at its own orbit. The moon plays a significant role in shaping Jupiter's magnetic environment. Every second, about 1 ton of material is ejected into space from Io's volcanic plumes, creating a plasma torus that surrounds the planet. This interaction does more than just power Jupiter's mesmerizing auroras. It contributes to a complex electromagnetic system that challenges everything we know about planetary magnetospheres. Io's impact on Jupiter's magnetosphere exemplifies how interconnected these celestial bodies are. The implications of studying Io extend far beyond the immediate confines of our solar system. While the moon itself is too inhospitable for life as we know it, its active volcanic processes open the door to broader questions about the conditions under which moons and planets might host life, or, at the very least, survive extreme environments. By studying Io, scientists can refine their models of celestial dynamics, deepening our understanding of what makes certain environments more likely to support life. Looking to the future, missions like the European Space Agency's Jupiter Icy Moons Explorer, scheduled to launch in the 2020s, and NASA's Europa Clipper will further investigate Io and its fellow Galilean moons. These missions will offer even more revelations about Io's volcanic activity, its interaction with Jupiter's magnetic field, and its broader role in the Jovian system. Through these upcoming explorations, Io will continue to challenge our understanding of where geological forces can thrive, furthering our knowledge of the dynamic processes shaping celestial bodies. In the grander scheme of space exploration, Io is a symbol of the untamed, active forces that shape moons across the universe. Its study not only enriches our understanding of the solar system, but also offers critical lessons about the forces that mold planets and moons. Perhaps most importantly, Io reminds us that the universe is full of places where wonder and discovery can occur, worlds unlike our own, yet intricately connected to the story of our own existence. Saturn's moon Titan stands as one of the most captivating and mysterious worlds in our solar system, a beacon for scientists and space enthusiasts. As the largest moon of Saturn and the second largest in the entire solar system, Titan is not only vast, but uniquely complex. The moon's dense atmosphere, thicker than Earth's, is composed primarily of nitrogen, with traces of methane and hydrogen. This thick veil of gases hides Titan's surface from visible light, compelling scientists to use radar and infrared instruments to reveal its hidden secrets. What truly sets Titan apart from other moons is its extraordinary weather system. Unlike any other world we know, Titan experiences its own version of Earth's hydrological cycle, yet with a chilling twist. Instead of water, Titan's rivers, lakes, and seas are filled with liquid methane and ethane, substances far colder and far more alien. Despite its frigid surface temperature, which averages a bone-chilling -179 degrees Celsius, -290 degrees Fahrenheit, Titan shares with Earth the processes of evaporation, cloud formation, and precipitation, shaping its unique landscape. The surface of Titan is as varied as it is alien. Vast, shifting dunes of hydrocarbon sands stretch across its equator, while jagged mountain ranges rise above the horizon. At the poles, a multitude of liquid hydrocarbon lakes dot the landscape, making this moon one of the most active and intriguing bodies in the solar system. The discovery of these liquid bodies has positioned Titan at the forefront of the search for extraterrestrial life. The potential for prebiotic chemistry, the building blocks of life, has made Titan a focal point for scientists looking beyond Earth. The Cassini-Huygens mission, a groundbreaking collaboration between NASA, the European Space Agency, ESA, and the Italian Space Agency, ASI, has played a crucial role in unveiling Titan's secrets. When the Huygens probe descended onto Titan's surface in 2005, it provided humanity's first close-up view of this enigmatic moon. What it revealed was astonishing. A world shaped by erosion, with river channels and stones smoothed by the flow of liquid methane. The images from the probe opened up new questions about Titan's geological history, its climate, and the possibility of life beneath its icy surface. Further exploration of Titan has sparked even more intrigue. Beneath its icy crust lies a subsurface ocean, potentially a mixture of water, salts, and ammonia, that may harbor conditions conducive to life. The interaction between this hidden ocean and Titan's rocky mantle could create chemical environments capable of supporting the reactions necessary for life. The prospect of such a subsurface ocean has made Titan a key target for astrobiologists, particularly those exploring the potential for life beyond Earth. Titan's thick, organic-rich atmosphere acts as a natural laboratory for studying the chemistry that could occur on other exoplanets with similar conditions. Driven by sunlight and possibly by cryovolcanism, Titan's atmosphere is a hotbed of complex organic chemistry, producing compounds that may be precursors to the more sophisticated molecules associated with life. The chemical processes on Titan not only provide insight into the moon itself, but also offer clues about the broader processes that could take place on other worlds in the universe. The search for answers continues. Future missions, such as NASA's Dragonfly mission, slated for launch in the 2030s, promise to deepen our understanding of Titan's chemistry and its potential for habitability. Dragonfly, a rotorcraft designed to fly through Titan's dense atmosphere, will cover far more ground than a traditional lander or rover ever could. Its objectives include studying prebiotic chemistry, exploring Titan's surface and subsurface, and investigating its atmospheric and geological processes. By directly sampling Titan's environment, Dragonfly aims to unlock the moon's secrets, potentially reshaping our understanding of life's origins. Could Titan, with its organic-rich atmosphere and diverse chemical processes, hold the key to life beyond Earth? The answers may lie in the moon's vast hydrocarbon lakes, its frozen oceans, and its unique weather systems. Answers that could revolutionize our understanding of life in the universe. Oumuamua, an object so intriguing it quickly became the subject of intense scrutiny, captivating the minds of scientists and stargazers alike. Discovered on October 19, 2017, by astronomers using the Pan-STARRS 1 telescope in Hawaii, its arrival marked a historic moment in astronomical discovery. Its name, Oumuamua, drawn from the Hawaiian word meaning scout or messenger from afar arriving first, aptly reflects its unique position in the history of our understanding of the cosmos. It wasn't just any asteroid or comet. It was the first known interstellar object to pass through our solar system. What immediately set Oumuamua apart from every other celestial body was its strikingly elongated shape, a feature unlike anything previously observed in our solar system. Measuring roughly 800 meters in length and a mere 80 meters in width, its cigar-like form defied expectations. But this wasn't the only mystery it presented. As it journeyed away from the sun, Oumuamua exhibited a strange acceleration, behavior inconsistent with natural celestial objects, which typically slow down as they move farther from the sun. Most notably, it did so without the usual telltale signs of outgassing, such as a comet's tail. Its surface, deep red in color, suggested it had been exposed to cosmic rays for millions, if not billions, of years. This unusual surface coloring hinted at the possibility of organic molecules that had undergone cosmic irradiation throughout its long and solitary existence. However, one of the most perplexing aspects of Oumuamua was its lack of a clear origin. Its trajectory pointed to the fact that it had been ejected from another stellar system long before it made its brief, enigmatic passage through ours. As scientists studied Oumuamua, questions mounted. Some speculated that its unexpected acceleration could be due to outgassing, the same process that propels comets. However, with no visible tail or coma, this theory seemed increasingly unlikely. This opened the door to more exotic ideas, including the suggestion that Oumuamua might not be a natural object at all. Could it be an artificial probe? An interstellar relic sent from a distant civilization? The very possibility sparked a global debate. But the mysteries didn't stop there. One of the more astonishing discoveries was that Oumuamua was tumbling through space, rather than rotating smoothly. Its brightness fluctuated dramatically, a clue that it was not perfectly cylindrical, but likely flat or extremely elongated. Such erratic behavior suggested a violent past, perhaps a collision that had sent it careening through space long before it arrived in our solar system. The question of Oumuamua's origin remained equally elusive. While it was clear it came from outside our solar system, pinning down its exact point of origin was a daunting task. Some theories suggested it could be a fragment from a larger object, shattered during a close encounter with a star or planet. Others posited it might be a remnant of a planetary building block, a piece of a planet that never fully formed. The variety of theories reflected both the limited data available and the unprecedented nature of such a discovery. Oumuamua's fleeting visit revealed the limitations of our current astronomical technologies, underscoring the need for more advanced systems to track and study interstellar objects. It also sparked new initiatives within the scientific community, leading to proposals for missions that could intercept or even rendezvous with future interstellar visitors. These missions could offer unprecedented opportunities for direct study and might hold the key to answering long-standing questions about the composition of other star systems. Reflecting on Oumuamua's brief passage through our solar system, its impact on astronomy is undeniable. It has sparked vital conversations about the importance of global cooperation to monitor the skies for future interstellar objects. More importantly, it has opened up new frontiers in our understanding of the universe. As our technology advances, we stand on the precipice of a new era in space exploration, one where the mysteries of the cosmos may soon be within our reach. Oumuamua may have been just a visitor passing through, but its legacy will likely shape the future of our understanding of the universe for years to come. Eris, a distant and enigmatic world, lies far beyond the familiar boundaries of our solar system. Discovered in 2005, this icy giant not only captured the imagination of astronomers, but also became a catalyst for one of the most significant debates in planetary science. Eris's discovery directly contributed to the reclassification of Pluto, changing its status from planet to dwarf planet. But Eris is far more than just a trigger for that controversy. It offers a fascinating glimpse into a remote region of space that holds countless mysteries. Located in the scattered disk, an isolated and sparsely populated area of the solar system, Eris orbits the Sun at a staggering distance, taking nearly 558 years to complete a single revolution. This solitary and slow journey paints Eris as a quiet sentinel on the outer rim of the solar system. Named after the Greek goddess of discord and strife, Eris lives up to its mythological namesake, having sparked a tempest in the astronomical community. With a diameter of 2,326 kilometers, Eris is slightly smaller than Pluto, but boasts a remarkable density, hinting at its rocky and icy composition. This composition reveals clues about the early materials and conditions of the solar system's outermost realms. One of the most striking features of Eris is its gleaming surface, which reflects an unusual amount of light. This intense reflectivity suggests that the dwarf planet is shrouded in a thin layer of frozen methane. The brightness of Eris's surface is not static. It fluctuates as the planet moves along its orbit, likely due to the sublimation of ice into gas. As Eris recedes from the Sun, this process alters the reflectivity, creating a dynamic, ever-changing surface. Eris is not alone in its distant orbit. It has a single moon, Dysnomia, named after Eris's daughter in Greek mythology, who represents lawlessness and chaos. The discovery of Dysnomia was pivotal in estimating Eris's mass, revealing that it is about 27% heavier than Pluto. This information deepened our understanding of Eris's physical characteristics and composition, providing scientists with a clearer picture of the object's density and internal structure. Yet, Eris's significance extends beyond its physical attributes. The discovery of this distant world ignited a fundamental shift in our understanding of what constitutes a planet. In 2006, the International Astronomical Union, IAU, revised its criteria for planethood, leading to Pluto's demotion. The new definition required a celestial body to orbit the Sun, be spherical in shape, and have cleared its orbit of debris. Eris, residing in the vast Kuiper belt, challenges this notion of orbital dominance. The sheer number of icy objects in this region forced the creation of the dwarf planet category, forever altering our understanding of the solar system's hierarchy. As we venture deeper into the science of Eris, we uncover more mysteries that extend beyond its role in planetary reclassification. The question of its atmosphere is one of the most captivating aspects of this distant world. Early observations suggest that Eris may possess a tenuous atmosphere composed of nitrogen and methane, much like Pluto. But this atmosphere behaves differently from those of planets in the inner solar system. As Eris moves closer to the Sun, its atmosphere expands, only to freeze back onto the surface as the planet drifts farther into the frigid depths of space. This dynamic atmospheric cycle is a valuable window into the workings of extremely cold environments. offering scientists insights into the behavior of gases under extreme conditions. Eris's orbit, which extends to a staggering 97 astronomical units from the Sun, places it in a region of space that is incredibly difficult to study. The immense distance from Earth makes direct observations challenging, but the interest generated by the New Horizons mission to Pluto has sparked excitement about future missions to explore Eris and its neighbors in the scattered disk. A mission to Eris could not only reveal more about this mysterious world, but also illuminate the nature of the scattered disk itself, an enigmatic zone teeming with icy bodies that remain largely unexplored. The study of Eris and its counterparts, such as Pluto and Haumea, is essential for expanding our knowledge of the diverse objects that populate the outer solar system. These dwarf planets each possess unique features that provide clues about the early formation of the solar system and the processes that continue to shape these distant worlds. By comparing the atmospheres of Eris and Pluto, for example, scientists can learn how these distant bodies evolve in response to their elliptical orbits and far-flung positions relative to the Sun. The tale of Eris is not just the story of one isolated celestial body, but rather a narrative that reshapes our understanding of the solar system. From its reflective surface to its tenuous atmosphere and distant orbit, Eris remains a testament to the mysteries waiting to be uncovered in the outer reaches of space. Looking to the future, Eris emerges as a key player in unraveling the mysteries of the solar system's formation and evolution. Its composition, particularly the unique ratio of rock to ice, holds the potential to unlock critical secrets about the materials that populated the outer solar system during its early history. But it's not just about what Eris is made of, it's also about the surface features that tell a deeper story. Craters and the possibility of cryovolcanoes could offer a glimpse into the impact, history, and the internal processes shaping this remote dwarf planet. With the rapid advancements in telescope technology and the growing possibility of dedicated missions to the Kuiper Belt and beyond, the horizon for Eris exploration is expanding. The James Webb Space Telescope, with its unparalleled sensitivity and resolution, is poised to unveil new views of Eris. Features that have long remained hidden could now be brought into focus. This may be our best chance to truly understand the distant realm of Eris. But Eris is not alone in this vast, uncharted territory. Sedna, another enigmatic object in our solar system, takes us on a journey through the far reaches of the solar system, where only a handful of explorers have ventured. Discovered in 2003, Sedna's orbit is one of the most distant and eccentric, drawing it from a mere 76 astronomical units AU from the Sun to an astonishing 936 AU at its farthest point, an extraordinary 11,400-year journey. Its strange orbit challenges our understanding of how the solar system formed and how the farthest regions are shaped by gravitational forces. Though smaller than Pluto, Sedna is considered a dwarf planet with a diameter of about 1,000 kilometers. Yet it remains in a curious position, its classification still debated by the International Astronomical Union. One striking feature of Sedna is the intense redness of its surface, hinting at the presence of complex organic molecules, such as tholins. These compounds form when ultraviolet sunlight interacts with simple organic molecules like methane and ethane, a clue that this faraway object might be more familiar than we think. The discovery of Sedna itself was groundbreaking. It resides in a region of space once thought to be a vast, empty void. Yet its presence, and the discoveries of similar objects since, suggests the existence of a previously unknown population of bodies in the outer solar system, sometimes referred to as the inner Oort cloud or sednoids. These bodies could be ancient remnants from the early solar system, offering critical insights into its formation and the distribution of small objects far beyond Neptune. What makes Sedna even more intriguing is its odd orbit, which doesn't bring it close enough to be influenced by Neptune or the other giant planets. This raises a compelling possibility that Sedna might have been perturbed by a massive, yet undiscovered object lying far beyond Neptune, or perhaps it was captured from another star during the Sun's early history in a dense star cluster. This mystery has sparked a wave of excitement among astronomers, as the peculiarities of Sedna's path through space may hold the key to understanding the hidden forces at play in the outer reaches of the solar system. One of the most tantalizing theories surrounding Sedna's discovery is the suggestion that it may be influenced by a potential ninth planet, often referred to as Planet 9. This hypothetical world could be several times the mass of Earth and may be lurking undetected in the dark, cold regions far beyond Neptune. If it exists, Planet 9 might be exerting a gravitational pull on Sedna and other distant objects, causing their odd orbits. As the search for this elusive planet intensifies, complex simulations and observations are guiding astronomers as they strive to uncover the truth behind the anomalies in Sedna's orbit. Sedna's long, winding journey around the Sun also offers an invaluable opportunity to explore the Sun's influence over vast distances. As Sedna moves closer to the Sun, it could develop a faint coma, much like comets do when they approach our star. This could provide crucial insights into the composition of Sedna and how distant bodies interact with solar radiation and the solar wind. Even at the extreme distances Sedna reaches, the Sun's presence continues to shape its journey, a fascinating reminder of how interconnected the entire solar system truly is. In the coming years, the mysteries of both Eris and Sedna could reveal new layers of understanding about our solar system, its formation, and the forces that continue to shape its distant, icy realms. Moreover, Sedna's existence disrupts our conventional understanding of the solar system's early dynamics. It forces us to refine our models, revealing a past much more chaotic and complex than we initially imagined. Scientists have long speculated that the Sun was once part of a dense star cluster, where gravitational encounters with neighboring stars could have dramatically altered the orbits of distant objects in our solar system. Sedna, with its extreme and elliptical orbit, seems to support this hypothesis, offering a rare glimpse into the chaotic forces that might have shaped the outer reaches of our cosmic neighborhood. Yet, Sedna's mysterious orbit might also suggest another story. Some researchers propose that its path could have been influenced by unseen celestial bodies, perhaps even a passing star that interacted with Sedna in its early days. If true, this would paint an even more chaotic picture of the early solar system, where unpredictable forces were at play. The exploration of Sedna itself represents the relentless drive of humanity to understand the unknown. As we continue to probe the mysteries of this distant world, we uncover new questions that push the boundaries of our scientific knowledge. Each discovery reveals new facets of our solar system's formation and the forces that have shaped it over billions of years. Sedna is a time capsule, preserving the secrets of an era when the solar system was still in its formative stages. Looking ahead, future missions, perhaps involving flybys or even orbiters, could unlock even more of Sedna's secrets. Such missions could offer unprecedented insights into the outer reaches of our solar system, challenging our understanding of planetary formation, orbital dynamics, and the forces at play in the distant cold regions of space. In time, we may uncover just how Sedna fits into the greater narrative of our cosmic evolution. Now, consider the intriguing world of Kepler 1625b. Discovered by the Kepler Space Telescope, this exoplanet has captivated the imagination of astronomers and the public alike. Located in the constellation Cygnus, approximately 4,000 light-years away, Kepler 1625b orbits its star, Kepler 1625, in a period of just 287 days. The star itself is a larger, older version of our Sun, creating an environment that places Kepler 1625b in the habitable zone of its star, an area where liquid water might exist, potentially fostering the conditions for life. Kepler 1625b is classified as a hot Jupiter, a gas giant several times the size of Jupiter itself. These types of planets are known for their extreme temperatures and dense atmospheres, which make them fascinating targets for study. But what sets Kepler 1625b apart is not just its size or position, but the potential discovery of something far more remarkable: the existence of a moon orbiting the planet. This potential exomoon, dubbed Kepler 1625bi, could be a game changer. If confirmed, it would be the first ever moon discovered outside our solar system, and it could redefine our understanding of moon formation. What makes this discovery particularly exciting is the size of the proposed moon, estimated to be comparable to Neptune. No such moons exist in our own solar system, and the idea that such a large moon could exist challenges many of the theories we've held about how moons form around their parent planets. The process of detection was nothing short of groundbreaking. Astronomers identified the potential exomoon through transit observations, where the planet and its moon pass in front of their star, causing a temporary dimming of the starlight. This dimming effect allows scientists to measure the size and gravitational influence of the moon. Through careful analysis, they noted that the moon's gravity seemed to affect the timing of Kepler 1625b's orbit, further suggesting the moon's presence. As you can imagine, this discovery has sparked intense debate among the scientific community. While the evidence is compelling, more observations and analysis are needed to confirm the moon's existence. Yet, even if it turns out to be a false alarm, the mere possibility of such a moon challenges our preconceived notions about the structure of planetary systems. If the exomoon's existence is confirmed, it could revolutionize our understanding of moon formation. The dynamics of a giant moon orbiting a gas giant in a distant solar system present a scenario completely different from the moons of our own solar system. It could offer clues about how moons form in the presence of a giant planet, and it may even provide insights into the processes that led to the formation of our own moon. What's more, the discovery of such a moon could have significant implications for Kepler 1625b itself. The presence of a massive moon could alter the planet's internal structure, its atmosphere, and even its potential for habitability. If the exomoon were to be confirmed, it would offer a unique opportunity to study the interactions between a planet and its moon in a completely different environment from anything we've observed in our own solar system. In the end, the discovery of Kepler 1625b and its potential exomoon speaks to the limitless possibilities that await us beyond our home planet. Every new exoplanet, every potential moon, every new discovery pushes the frontier of our knowledge just a little further. And in doing so, it brings us closer to understanding not just the cosmos, but our place within it. Gravitational forces, subtly yet powerfully, dance between the planet and its moon, shaping the rotational dynamics of both celestial bodies. These forces could trigger tidal heating, which in turn influences the moon's internal geology and atmospheric conditions. Such an interaction isn't just a scientific curiosity, it sparks the question, could this exomoon, affected by such forces, harbor the conditions necessary for life? While Kepler 1625b, a gas giant, is unlikely to host life, its moon presents a tantalizing possibility. If this moon possesses a rocky surface and an atmosphere, could it become a cradle for life? Perhaps in ways we've only theorized? This potential, this fleeting chance for habitability, adds a captivating new layer to the search for extraterrestrial life. It shifts our gaze not only to distant planets, but toward their moons, expanding the search for life beyond the conventional. But how do we confirm such possibilities? The quest for understanding this exomoon involves sophisticated tools and cutting-edge space missions. Instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope are pivotal in this search. With their high-resolution imaging and advanced spectroscopy capabilities, these telescopes allow scientists to detect and characterize exoplanets and their moons across vast cosmic distances. Paired with the precision of computer modeling, these observations give us a window into the complex planetary systems like that of Kepler 1625b, unraveling their formation, evolution, and potential for life. Then there's Kelt 11b, a striking exoplanet discovered by the Kilodegree Extremely Little Telescope Survey, known for uncovering exoplanets around bright stars. Located about 320 light-years away in the constellation Sextans, Kelt 11b orbits Kelt 11, a star nearing the end of its life cycle. This unique positioning offers scientists an extraordinary opportunity to study the planet's atmospheric composition in fine detail. Kelt 11b, often dubbed a hot Jupiter, is a gas giant that bears some resemblance to our own Jupiter, but with a crucial difference. It orbits incredibly close to its star, resulting in scorching surface temperatures that exceed anything seen in our solar system. Yet what sets Kelt 11b apart from other hot Jupiters is its incredibly low density. So low, in fact, that the planet is almost as inflatable as a balloon. This astonishing feature suggests a highly extended atmosphere, making it an exceptional target for atmospheric studies. Its orbit is swift, completing a full revolution in just under 5 days. And this proximity subjects Kelt 11b to intense stellar radiation, heating its surface to extreme temperatures. The radiation, relentless and powerful, likely causes atmospheric escape, the process by which the outer layers of a planet's atmosphere are stripped away by the force of stellar winds and radiation. Kelt 11b's large size, nearly 40% larger than Jupiter despite its lower mass, and its extended atmosphere provide an unparalleled opportunity to probe the chemical composition of its atmosphere. Through transmission spectroscopy, scientists can analyze the starlight passing through the planet's atmosphere during transits, revealing the presence of molecules such as water vapor, carbon monoxide, and other key compounds. These findings hold the potential to deepen our understanding of how exoplanets form and evolve under the intense conditions of their star's radiation. What makes Kelt 11b especially fascinating, however, isn't just the data we collect. Its remarkable characteristics, its low density and extended atmosphere, serve as a crucial example for understanding the physics and chemistry of hot Jupiters. These insights are vital for piecing together the evolutionary puzzle of gas giants, especially those subject to extreme stellar irradiation. Through these studies, we gain valuable clues about the atmospheric retention, heat distribution, and the potential for atmospheric escape over time. One of the most profound lessons Kelt 11b offers lies in its atmospheric life cycle. Exposed to such extreme conditions, its atmosphere undergoes processes unlike those observed in more compact and dense planets. Atmospheric escape is a prominent feature on Kelt 11b, with lighter molecules being stripped away at an accelerated rate by the relentless radiation of its nearby star. This process, playing out in real time, offers scientists a rare glimpse into the dynamic and transformative forces shaping planetary atmospheres across the cosmos. And so, this process provides scientists with invaluable insights into how planets lose their atmospheres over time. By examining these transformations, we gain a deeper understanding of the timescales over which such atmospheric changes occur and the profound implications these shifts hold for the potential habitability of planets. The atmospheric study of Kelt 11b through transmission spectroscopy offers a remarkable view into the chemical and thermal dynamics of hot Jupiter atmospheres. By detecting specific molecules and observing their distribution, scientists can also examine how these molecules interact with incoming stellar radiation, adding depth to our models of atmospheric behavior and chemistry. These models, in turn, serve as key tools for predicting the atmospheric conditions of planets yet to be observed in detail, expanding our comprehension of planetary atmospheres across the galaxy. But the significance of this research does not stop there. It emphasizes the critical role of future telescopic missions and the ongoing development of cutting-edge observational technologies. Instruments like the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescopes, ELTs, are on the cusp of unveiling even more intricate observations of Kelt 11b, alongside other exoplanets. These state-of-the-art tools will allow scientists to detect fainter signals and identify more complex molecules in the atmospheres of distant worlds, further refining our understanding of their composition and dynamic behavior. Now let's shift our focus to the HR 8799 system, an extraordinary and groundbreaking discovery that has revolutionized our understanding of planetary systems. Located about 129 light-years away in the constellation Pegasus, this system revolves around 8799, a young and slightly more massive star than our own Sun. The HR 8799 system holds a place of particular significance in the field of astronomy for being one of the first to allow the direct imaging of multiple exoplanets, an achievement that stands as a milestone in the study of distant worlds beyond our own solar system. Discovered between 2008 and 2010, the HR 8799 system features 4 massive exoplanets, HR 8799E, D, C, and B. These gas giants, each weighing between 7 and 10 times the mass of Jupiter, move along orbits far from their parent star. Their distances from the star vary, with the outermost planet, HR 8799b, orbiting at a distance similar to Pluto's orbit in our own solar system. One of the most remarkable aspects of the HR 8799 system is how its planets were directly imaged, an achievement made possible by sophisticated telescopes equipped with adaptive optics systems. These systems, designed to correct for the blurring effects of Earth's atmosphere, allow astronomers to capture clearer, more detailed images of celestial objects. Unlike most exoplanets, which are typically detected using indirect methods like transit or radial velocity techniques, the HR 8799 planets were observed directly. These direct observations have provided astronomers with invaluable data about their atmospheres, compositions, and orbital dynamics. The planets themselves are young, approximately 30 million years old, and continue to glow with residual heat from their formation. This heat makes them easier to observe using infrared telescopes, revealing complex atmospheres with clouds and perhaps even weather systems, not unlike those found on the gas giants of our solar system. Adding to the intrigue, the HR 88799 system is encircled by a vast debris disk composed of dust and ice. This disk is thought to be the remains of the material that helped form the planets, and may even indicate the presence of smaller, less undiscovered bodies within the system. As we continue to explore the HR 8799 system, we find ourselves on the brink of further revelations. The scientific significance of these findings is immense, offering new windows into planetary formation, atmospheric science, and dynamics of young planetary systems, promising a future full of potential discoveries. The HR 8799 system, with its remarkable direct imaging, opens an extraordinary window into the universe. This unique capability allows astronomers to delve deep into the atmospheric composition, orbital mechanics, and even the climate of its exoplanets, offering a wealth of information about the processes that shape planetary systems and how they evolve over time. But it is the planet's atmospheres that particularly captivate scientists. Through spectroscopic analysis, the study of the light emitted or absorbed by these planets, we can unlock the secrets of their chemical makeup. This technique reveals the presence of key gases such as water vapor, methane, and carbon monoxide, offering clues about not just their chemical composition, but also the dynamics of their weather systems and climate. The detection of these substances is more than just a confirmation of theories. It deepens our understanding of the forces at play in the atmospheres of gas giants, potentially guiding us toward insights on planetary weather patterns far beyond our own solar system. Then there's the debris disk surrounding the HR 8799 system, a critical puzzle piece in the story of planetary formation. By analyzing the disk's structure and composition, scientists can infer the existence of smaller bodies, such as asteroids or comets, which may have played a role in shaping the planets. This debris disk is not just a remnant of cosmic history. It offers a glimpse into the late stages of planetary formation, shedding light on the processes that could have occurred during the infancy of our own solar system. Looking ahead, the future of studying HR 8799 is deeply intertwined with the advancement of telescope technology, with groundbreaking instruments like the James Webb Space Telescope, JWST, and cutting-edge ground-based telescopes equipped with next-generation adaptive optics. Astronomers are poised to capture even more intricate details of the system. These innovations will enhance our ability to explore the composition, temperature profiles, and potential weather patterns of the HR 8799 planets in unprecedented detail, offering a clearer view of their atmospheres and the mysteries they hold. Moreover, the study of this distant system holds broader implications for the search for life beyond Earth. While it is unlikely that the gas giants themselves could harbor life as we know it, their detailed study helps us understand the environmental conditions that may exist in other planetary systems. By unraveling the formation and evolution of gas giants and their moons, we are gaining valuable insights into the factors that might influence the habitability of distant worlds. These findings may one day inform our search for life elsewhere in the galaxy. As we conclude this documentary, we are reminded of the vast, uncharted territories of the cosmos, each discovery leading us closer to unraveling the universe's mysteries. With every technological breakthrough and every new observation, we inch forward in our understanding of the universe and our place within it. The journey of discovery continues, and with it, the potential for new and extraordinary revelations. What awaits beyond the next horizon? Only time and our relentless pursuit of knowledge will reveal the answers. But one thing is certain: the greatest discoveries are yet to come. Thank you for joining us on this remarkable journey.